All right, let's get right into it. There's this one number that just drives physicists crazy. It's a constant that seems to be woven into the very fabric of our reality. Everything from how light zips across the universe to how atoms hold themselves together. But here's the kicker. For over 100 years, nobody's had a clue why it is what it is. It's truly one of the biggest mysteries in all of science.
So that's the big question, right? Why this specific number? Was it just a random roll of the cosmic dice, a number we just have to accept and move on? Or is there something deeper going on? A kind of blueprint hidden in the structure of space-time itself? Well, a really fascinating new theory is suggesting it's exactly that.
And there it is, roughly 137, it's called the fine structure constant. And physicists have measured this thing with unbelievable precision. But where it comes from has been a total black box. It just is, or at least that's what we thought.
Now, to be super precise, we're actually talking about the inverse of the fine structure constant. It's a pure number, no units, and it basically sets the dial for the strength of electromagnetism. And you have to understand, if this number were just a tiny bit different, the universe as we know it, with stars, chemistry, us, it just wouldn't exist. This isn't just some random number, it's the master tuning knob for our entire reality.
Okay, so this brings us to a pretty wild new idea. What if 137 isn't some abstract, weird quantum number? What if it's actually a physical, mechanical property of the vacuum of space? Like, what if we could calculate it based on the actual stiffness of space itself, derived from its basic geometry?
To even consider that, we have to totally shift how we think about spacetime. So forget the old picture of a smooth, empty stage where things happen. This new model says to imagine spacetime as a real physical material. A jammed substance made of countless tiny Planck-scale grains, almost like a super stiff foam. And if that's true, it changes everything.
The beautiful thing about this new theory is how simple the logic is. It builds the number 137 in just 3 easy steps. First, you figure out the absolute maximum stiffness spacetime could possibly have if it were a perfect system. Then you subtract a little penalty because, well, it's messy and disordered. And finally, you subtract one last tiny bit to account for a sort of microscopic jiggle in the structure. That's the whole recipe.
So, step 1, let's figure out that maximum possible stiffness. I want you to think of this as the universe's theoretical hardware limit. If the fabric of spacetime were a perfectly ordered, perfect crystal, what would its stiffness be?
Well, the theory calculates that this absolute maximum value is 138.24. And this isn't a random guess. It's a number that pops out directly from the geometry of this granular network. This number represents the raw, untapped potential of the vacuum, before we start accounting for all of reality's little imperfections.
So you're probably asking, where on earth does that number come from? Well, it's a 4-step process. First, the model treats spacetime like a discrete network. Second, the stiffness of that network scales with the square of how many neighbors each little grain has. We'll call that Z. Third, basic geometry tells us that for the densest possible messy arrangement, Z is exactly 14.4. And finally, you average all that over 3D space, which gives you a factor of 2/3. You put all of that together, and boom, 138.24. No fudging numbers, just pure geometry.
Okay, so the theoretical speed limit is 138.24, but we know the real number is about 137. Clearly, the universe isn't running at its max potential. It seems there's a price to pay for being imperfect, for being part of the real world.
Which leads to the obvious next question, right? If the hardware can handle 138.24, why is reality tuned lower? Well, the answer is that the vacuum of space isn't a perfect, neat crystal. It's disordered, it's messy, and that messiness has a cost. That first penalty is a deduction of exactly 1.20. The physicists behind this call it the frustration tax, and it is the single biggest reason why the real value isn't 138.24.
And honestly, the concept here is just brilliant. Think about it. A perfect crystal is the lowest energy, most stable state something can be in. But the vacuum, it's stuck in a messy, glassy state. It's frustrated because it can never quite settle into that perfect order. So this tax of 1.2 is literally the energy cost of that permanent, built-in disorder. It's the price of being messy.
But we're not done just yet. There is one final, really tiny correction we have to make. After we subtract that frustration tax, we're at 137.04. I mean, that's already incredibly close, but it's not perfect. We need to subtract another 0.0048.
This last little piece of the puzzle is called the compliance flicker. The idea is that in a messy material, the individual grains can't move in perfect unison. They kind of jiggle and shift around on a microscopic level when under stress. This constant little flicker makes the entire structure just a tiny, tiny bit softer, a little less stiff, and that accounts for our final small deduction.
So, there we have it. We have our three ingredients. We've got the maximum capacity, we've got the tax for being disordered, and we've got the tiny correction for the microscopic jiggle. It's time to put them all together and see what this blueprint of the cosmos actually adds up to. Let's just walk through it one more time. We start with that maximum theoretical stiffness, the saturation capacity, at 138.24. From that, we subtract the frustration index, that 1.2 penalty for being a messy system. And then, we take away that last tiny compliance flicker of 0.0048. The big question is, what do we get?
And there it is. The theory predicts a value of 137.0352. The number we've actually measured in countless experiments is 137.035999, and so on. I mean, that's the aha moment right there. A number that we cooked up purely from geometric ideas matches reality with just breathtaking accuracy.
Just look at how close that is. The difference is only about 5 parts per million. That's a discrepancy of 0.0005%. To derive one of nature's most important numbers basically from scratch and get this close, that is an absolutely incredible achievement.
And this quote from the original paper really says it all. The most important phrase there is without arbitrary parameter fitting. What that means is they didn't just guess and plug in numbers until they got the right answer. No, they built a model from the ground up based on the geometry of a granular spacetime, and this number is simply what the model spit out.
So, what's the big takeaway here? What does this all mean? Well, if this theory holds up, it suggests that the fundamental constants of our universe might not be random at all. They might be the inevitable result of the universe's geometric structure. Maybe the cosmos isn't playing dice after all. Maybe it's just built on an elegant, predictable, and, well, mechanical blueprint. And that really leaves us with a final, tantalizing thought, doesn't it? If physics' most mysterious number turns out to be just a feature of the geometry of space, what else is hiding in that blueprint? What about gravity, or the mass of an electron, or the speed of light? Are they, too, just waiting to be read directly from the architecture of reality itself?